We're going to discuss the formulation of a linear regression problem. To formulate this problem, we're going to see there's a bunch of observation noise, and it's because the presence of observation noise that we'll adopt a probabilistic approach and explicitly model the noise using a likelihood function. More specifically, throughout this video, we consider a regression problem with the likelihood function if y given x is normally distributed with y given f of x at sigma squared. Here, x is a d-dimensional vector of inputs, and y is a real number of noisy target values. Equation: the functional relationship between x and y is given by y equals f of x plus epsilon, where epsilon is normally distributed with mean 0 and variance sigma squared, and is independently identically distributed. Our objective here is to find a function that is similar to the unknown function f that generates the data and also generalizes well to unseen data. I'm going to focus on parametric models. That is, we choose a parameterized function and find parameters theta that work well for modeling the data. For the time being, we assume that the noise variance sigma squared is known, and we focus on learning the model parameters theta. In linear regression, we consider a special case that the parameters theta appear linearly in our model. An example of linear regression is given by the probability of y given x and theta is normal distribution with mean y given x transpose theta variance sigma squared. If and only if y equals x transpose theta plus epsilon, where epsilon is normally distributed with mean 0 and variance sigma squared. The likelihood of the first equation is the probability density function y evaluated at x transpose theta. Since we know x and theta, the only source of uncertainty originates from the observation noise. Without the observation noise, the relationship between x and y would be entirely deterministic. This class of functions, f of x equals x transpose theta, is a class of straight lines passing through the origin. Here's an example. The graph illustrates the relationship between the amount of sugar in a candy and the rating of a candy. We model it with a straight line. Observation sat directly on the line, we would say that the model is deterministic. Essentially, there is no noise. The line that we have created here is of the form y equals mx plus b. The extent to which observations do not sit on the line is governed by the noise epsilon. Note that x, the sugar, is the independent variable. Y, the rating, is a dependent variable. Epsilon is the random deviation or the error in the model. Linear regression refers to models that are linear in parameters. The linear regression model here is not only linear in parameters, but it's also linear in the inputs. Models like y equals y transpose of x and times theta plus epsilon for nonlinear transformations phi are also linear regression models because linear regression refers to linear in parameters, i.e., models that describe a function by a linear combination of input features. Here, a feature is a representation phi of x of the inputs x. In this video, we discuss how to find good parameters theta and how to evaluate whether a parameter set works well.